I've given you the permission to record. So. Okay. All right. So let's start then. So I've graded your midterms. There were quite a few misunderstandings from what I saw in your papers. So I don't have time to go over the whole midterm, but at least let me talk about question 4. So where you have a curve gamma in a manifold M, and you have vector bundle E over M with connection nabla, and the dual bundle E star over M with connection nabla tilde. And you're supposed to show, first of all, that if I take a section of E along gamma, say S, and a section alpha of E star along gamma, okay. Then to show that DDT of, so if I look at any time t, alpha of t, that's a linear functional on the fiber at gamma t of E. So that can act on S of t, which is an element of the fiber E gamma t. So this gives you a function of t. The derivative of this function you're supposed to show is given by the along gamma for E star. So that's capital D tilde dt alpha acting on ST plus alpha t acting on the covariant derivative capital ds dt. Right. Now, we know for a section of E over M, say sigma and a section of E star, say beta, and for X a vector field on M, the connection on the dual bundle, it satisfies the following Leibniz rule. So beta acts on sigma to give me a function on M, and X is a vector field which acts on that function on M. So X of beta of sigma, this by definition of the dual connection is nabla tilde X beta acting on sigma plus beta acting on nabla X sigma. Okay. We know this. Now, You want to use this to prove this equation here involving covariant derivative along curves. Now, what some people wrote is that, given a point gamma t along the curve, you can choose a vector field near that point whose value at gamma t is equal to gamma prime t. And then you simply apply this equation and you'll get this. The problem with that is that the sections along curves are not in general given by restricting a section on the manifold to the curve. We talked about this earlier, right? This section S, this is not of the form sigma composed with gamma. And this section alpha, this is not of the form beta composed with gamma, even locally. What is true is that S you can write as a sum of sections of E on the manifold restricted to gamma. So SIs, these are a local basis of E. Okay, so locally you can write S as summation AI of T, SI of gamma T. Okay, this is S of T. Locally, where SI is a local basis of E. And similarly, alpha T, I can write in terms of, so the basis SI gives a dual basis SI star. This is the dual basis to SI. Okay. So this is a local basis of E star. So alpha I can also write as some summation BI of T, SI star composed with gamma of T locally. So what do I mean when I say locally? What I mean is that given a time T, I choose a neighborhood of T so that gamma maps that neighborhood of T into a small open set where I have a local basis of E. Okay. Right, my bundle E is locally trivial, so I have a local basis on a small enough open set. And so if I choose T so that in an interval which maps into that small open set, there I can write any section as a linear combination of the local basis. And so a section along the curve will be given by a linear combination where the coefficients are functions of T. These are not functions on the manifold. These are functions of T. Okay. So is this clear? Yeah.
Yes, sir.
Okay. Now what do I know about the local basis and the dual basis? I know the following. I know that SI star of Sj, right? This is a function. The value of this at any point P, this is a constant, delta ij, independent of P, right? Okay. So, so if X is a vector field, then x of this SI star of Sj. On the one hand, this is 0 because this is a constant function. On the other hand, what is this? This is going to be nabla tilde x SI star applied to Sj plus SI star applied to nabla x Sj. Okay. So I have this equation. Now I look at the right hand side of the equation that I want to prove. So let me compute this d tilde alpha dt so applied to st will be what? So d tilde alpha dt applied to st, this will be, so from this equation alpha t in terms of SI stars, by linearity and the Leibniz rule for the covariant derivative along curves, this is going to be a sum over I. So you'll get dBi dt into SI star composed with gamma plus Bi into, now when I apply the covariant derivative to SI star, I can use the property of the covariant derivative that applied to a section restricted to the curve, it is given by the connection. So that will be nabla tilde, the connection in the direction of the curve. So nabla tilde sub gamma prime applied to SI star. Okay. Is this clear? Yeah. And this I'm applying to S of t. S of t is sum over j, aj, sj composed with gamma. Is this clear? So
Yes, sir.
Okay.
Sir, so if you have a point t naught, then for small enough epsilon, you can write this st as a sum ait del del xi, right? So if there is no intersection from t naught minus epsilon to t naught plus epsilon, then you can do that, and it is contained in a chart.
Yeah, but you could have infinitely many intersections, right? You could have a curve which intersects itself infinitely many times. You could have this. Just think of a graph where you take sine 1 over x and multiply it by e to the minus 1 over x squared. Right. This has infinite, it's a smooth function which has infinitely many zeros near the origin, right?
Okay.
So this could be your x coordinate and your y coordinate could be the same thing. You see what I mean?
Yeah.
So you will have infinitely many intersections in any point. So yeah, of course, at that point, gamma prime 0 has to be 0. But yeah, there could be many points where gamma prime 0 is 0, right?
Yeah. But our curves are smooth maps from
Yeah,
closed
this is a
intervals
smooth
to
map.
many.
This is a smooth map. This is a smooth map. This is a smooth map. Yeah. This is smooth. At t equal to 0, I just put this to be 0. This will be a smooth map. Absolutely smooth. This will be smooth.
Yeah, okay. Yeah, I'll think about it.
This is smooth. This is smooth. But this is for t not equal to 0. And you just put it to be 0, 0 for t equal to 0. This is smooth. Right?
Yeah. Hmm.
This is smooth. This is smooth. So yeah, curves don't have to have good behavior where their derivative vanishes. They could have infinitely many intersection points, self-intersections nearby. Okay. All right.
Yeah.
Yeah. So then in no neighborhood will you be able to write it with the coefficients being functions on the manifold. The coefficients have to be functions of t. Okay. Okay, so now what happens? So we have the sum over I, sum over j. So this will become a sum over ij. Right. Now the first term, you have si star acting on sj. So that is delta ij. So that will just give a sum over I, right? When I is equal to j. So that will give me sum over I dbi dt into aj, right? Okay. I get, into ai, sorry, into ai. Yeah, that will be the first term. And then I'll get another term, sum over ij, biaj into nabla tilde gamma prime si star acting on sj. So this thing is a function. This function evaluated at gamma, so composed with gamma. Okay. All right. Is that clear? And now let's look at the other term. So alpha of t applied to capital ds dt. So this will be what? This will be sum over I bi si star composed with gamma. The whole thing applied to sum over j. And now I'll have ds dt. So that again will become daj dt. Sj composed with gamma plus aj. And now I can use the compatibility of the covariant derivative along curves with the connection. So since the Sj is composed with gamma are given by restricting section of the manifold to the curve, then this becomes nabla sub gamma prime of Sj. Yeah. So now I apply this linear functional to this vector. And so, so when I apply this to the last term here, no, to the first term here, right? When I apply this to the first term here, this Si star with Sj again will give me delta Ij. So I'll only get the sum when I equal to j. And so I'll get the first term will be sum over I bi dai dt. Okay. Plus, then I'll get a sum over I sum over j biaj Si star applied to nabla gamma prime Sj. So this at gamma. Okay. So when I add up these two, what's going to happen? So d alpha d tilde alpha dt of ST plus alpha T ds dt will give me sum over I. So I'll get this dbi dt. So bi prime ai plus bi ai prime, okay, plus well, the other two terms, what will this give me? This is sum over ij. I'll get bi aj, and then inside, what will I get? Inside, I'll get, when I add these two up, what do I get? That's going to be the tangent vector gamma prime, right? Acting on the function SI star, so composed with acting on Sj. So that's going to be 0. What I'm saying is, when I add up these two terms, I'll get 0, right? This will be by the property we had here. For any vector field x acting on this SI star Sj is 0. So this sum, nabla tilde x SI star Sj plus SI star of nabla x Sj, this is 0 for any vector field x, right? So if I take any point P and I take a tangent vector at P, I can always choose a vector field x whose value at P is equal to that tangent vector. So this equation remains true if I replace x by any tangent vector at a point, right? So in particular, I can take that tangent vector to be gamma prime. That's what I have here. And so then this sum will be 0, right? So this sum is what? Nabla tilde gamma prime SI star. This acting on Sj plus SI star nabla gamma prime Sj. Okay, so I'm not writing the composed with gamma here because see, this gamma prime is a tangent vector at a point, right? So at the point gamma t. So this is going to act on SI star at the point gamma t, right? So this will be an element of the fiber of E star at gamma t that can only act on Sj at gamma t, right? On the value of Sj in the fiber of E at gamma t. Yeah. So here it's clear from the context that at which point this is acting. This is acting at the point gamma t. And similarly, this here, this is really SI star at the point gamma t acting on this vector in E at the point gamma t. Okay. So anyway, the sum of these two is 0, right? This sum is 0. So this term disappears. So what do you get? You get sum over I ddt of ai bi. So this is ddt of sum over I ai bi. And ai bi is nothing but alpha acting on S, right? Okay. Right, because S was summation ai si, alpha was summation bi si star. So alpha acting on S will be summation ai bi. Is that clear? Yes, is this okay?
Yes, sir.
Yeah, so that's the first part. And the second part, you have to show that if P, this is the parallel transport from, say, gamma 0 to gamma 1, right? So let me call PT, let's say, the parallel transport from gamma 0 to gamma T. Okay. And let me call PT tilde the parallel transport for the dual bundle. So E star gamma 0 to E star gamma T. So you have to show that PT tilde is equal to PT star inverse. Okay. So so for the proof, what do we do? So we take a vector in the fiber of E star at gamma 0. So let me call it, say, omega. And define a section alpha of the dual bundle along gamma by, so I want to define a parallel section whose value at time 0 is equal to omega. Okay. So I want to say that, so that parallel section, of course, should be given by PT tilde acting on omega, right? But I want to say that PT tilde is PT star inverse. So let me define the section using PT star inverse. If I can show that section is parallel, then I'm done, right? So I define alpha T to be PT star inverse of omega. So this will be in the fiber at gamma T of E star. Okay. So enough to show that alpha is parallel, right? Enough to show that d tilde alpha dt is identically 0, right? Okay. So how do we show this? We use part A. So use part A. So alpha t is PT star inverse of omega. So that means that PT star of alpha t is equal to omega, right? Yes. So where is omega? Omega is in E star gamma 0. Okay. So now let V be any vector in the fiber of E at gamma 0. Okay. Then apply both sides. These are linear functionals on E at gamma 0. So I can apply both of them to V. So then PT star alpha t applied to V is equal to omega V. And what is the definition of the dual linear map? This is alpha t applied to PTV, right? Yes?
Yes, sir.
And what is PTV? PTV I can think of as a parallel section S of E. Right? This is a parallel section of E along gamma. Right? Yes? Okay. So I'm getting that this alpha t composed with this parallel section ST, this is constant equal to omega of V. This doesn't depend on t. So therefore, 0 is equal to ddt of alpha t applied to ST. And this is equal to d tilde alpha dt applied to ST plus alpha applied to ds dt, but S is parallel. So the second term, this ds dt is 0. So this gives me just d tilde alpha dt applied to ST. Right? So this is 0. And now this S depended upon a choice of vector V in the fiber at gamma 0. So now you choose, let say E1 to EK be a basis of the fiber at gamma 0. You let SI of T be PT of EI. Okay. So then the SIs are parallel. So the SIs form a basis. SIs are the SIs are a basis of parallel sections of E along gamma. And we have that d alpha dt applied to SI of T. This is 0 for all I. Right? That implies that this d alpha dt, this is an element of the fiber E star gamma T that applied to a basis of E gamma T is 0. So therefore this linear functional is identically 0, right? So that means that d tilde alpha dt, this is the 0 linear functional in E star gamma T. So that's it. So that means alpha is parallel, and so we're done. Is this clear?
Yes, sir.
Okay, that's it. So, okay.
Sir,
Yes.
there's about a minute left, so I just want to ask you, shall I stop the recording before you leave the meeting, or? Like,
Yeah, you can stop the recording now. Yeah, it's fine. Yeah, you can stop it.
so
Thank you.
Will you start another meeting?
Yeah, I'll start another meeting.
Okay.
Yeah, you can stop recording.
Okay.
Thank you. So let's stop. Okay. So last time we started talking about volume on an oriented Riemannian manifold. So now M is an oriented Riemannian manifold. So that means the tangent spaces, each tangent space has a choice of orientation, and these choices of orientation are, in a sense, continuous. So then any tangent space, this is an inner product space with an orientation mu p, right? So that gives a volume form which is denoted by d vol m. So d vol m has the property that it takes the value 1. It's an n form which takes the value 1 for any positively oriented orthonormal basis EI of TPM, right? Okay. And we saw that if x1 to xn are local coordinates and G is the matrix of the Riemannian metric, so Gij is the inner product del del xi del del xj. So these are smooth functions in a neighborhood of P. Okay. Then this volume form can be written as the square root of the determinant of G into dx1 wedge dxj, dxn, right? Okay. Yes.
Yes.
Okay. Now, suppose that V and W are oriented n-dimensional inner product spaces. And T from V to W is a linear map. Okay. Then we can define its determinant to be the determinant of the matrix of T with respect to any positively oriented orthonormal basis EI Fj of V and W. Okay. So why is this well defined? Because the change of basis matrix, if I change the basis of V and the basis of W, because I'm only looking at positively oriented orthonormal basis, the change of basis matrix will be an orthogonal matrix whose determinant is positive, and therefore the determinant has to be 1, right? So the change of basis matrix, those have determinant 1. So therefore this determinant of the matrix of T is well defined. Is that clear? Yes?
Yeah, it's clear.
Okay. So the determinant of T is well defined. Now, what I want to look at is, so W has its volume form and V has its volume form. Both are non-zero n forms. So if I look at the pullback of the volume form of W, this is going to be some constant times the volume form of V, right? Yes. So how do I work out what this constant C is? This constant C is actually going to be turn out to be this determinant of T. So how do we see that? So this constant C, I can write as C devol V acting on E1 to En, right? Where EI is a positively oriented orthonormal basis of V. Now this C times devol V, this is T star devol W. So this acting on E1 to En, by definition of pullback, this is devol W acting on TE1 to TEN, right? Yes. Okay. Now this I can write as devol W of S F1 to S Fn, where S is the unique linear map from W to W, which sends the basis, say, Fi to TEI. Okay. All right. So what does that mean? That means that T I can write as S composed with U, right? From V to W, where U maps, U is the unique linear map from V to W. So here Fi is, Fj is positively oriented orthonormal basis of W, and U is the unique linear map which sends EI to Fi. So, right. So okay. So so this devol W of SF1 to SFN, S is a map from W to W. So we know how the top degree forms transform under endomorphisms. This will become determinant S, right? Into devol W of F1 to Fn. And since Fj is a positively oriented orthonormal basis, by definition of the volume form on W, this is 1. So this is determinant of S, right? And determinant of S will be the same as determinant of T, right? Because T is equal to S composed U, and U maps a positively oriented orthonormal basis to a positively oriented orthonormal basis. So, I mean, with respect to the bases, because matrix of T with respect to EI Fj is equal to the matrix of S with respect to Fj. Since T is equal to S composed with U and matrix of U with respect to EI Fj is the identity, right? Yeah, the matrix of U with respect to EI and Fj is the identity matrix. Is that clear? So the matrix of T will be the same as the matrix of U of S with respect to Fjs. Is this clear?
Yes, sir.
Yes. Okay. So that's it. So that means that this constant is nothing but the determinant of T. So therefore, the pullback of the volume form of W is nothing but determinant of T times the volume form of V. Okay. So T star of d vol W is equal to determinant T d vol V. Okay. So for example, if you have F, a smooth map between oriented Riemannian manifolds M and N, okay. And if I take U is a L1 function on N with respect to the volume measure d vol N, right? So the volume measure gives you a volume, the volume form of N gives you a volume measure which you get by integrating the volume form over open sets, right? So if I take an L1 function for this volume measure, right? Then I have this, so suppose this is a, suppose F is a diffeomorphism. C infinity diffeomorphism. And so suppose it's an orientation preserving C infinity diffeomorphism. So then the integral over N of U d vol N. So by properties of pullback, this is the same as the integral over M of F up the pullback form F star of U d vol N. Okay. Now the pullback of this form is you pull back the function and you pull back the volume form. So this will be integral over M. Pullback of the function is just the composition U composed F. And then you have F star of d vol N, right? So what will F star of d vol N be? So this is going to be by what we did earlier. This is just the pullback under the linear map df. So you'll get determinant of df into d vol M. Okay, so this will give you U composed F, determinant of df into d vol M. Okay. Is this all right? Yes.
Yes, sir.
Okay, so you get this change of variables formula for diffeomorphisms between Riemannian manifolds. Okay. All right, so now I want to talk about what's called the gradient of a smooth function on a Riemannian manifold, gradient vector field. Okay, so if F is so M is a Riemannian manifold. So if F is a smooth function, then at any point, its derivative dF at P, this is a linear functional, right? From TPM to R. But now TPM is an inner product space. So on an inner product space, you know that any linear functional is given by inner product with some vector, right? So there exists a unique vector which we denote by grad F at P. So this is an element of TPM such that DFP acting on any tangent vector V is given by the inner product of grad F at P with the vector V for all V in TPM, right? Does this make sense? Yes? Yes, is this okay?
Yeah, it's okay.
Yeah. So linear functionals on an inner product space are given by inner product with some vector, right? So in particular, the derivative dF at P, that is a linear functional. Therefore, it corresponds to some vector, right? Via using the inner product. So that vector is defined to be the gradient vector. Okay. That vector is defined to be the gradient vector. Now, how do you work out what this gradient vector is? So if I take local coordinates x1 to xn, okay. So suppose grad f, I can write this as summation some ai del del xi. Okay. And suppose I take a vector v, which is some summation bi or bj del del xj. So this is in TPM. Okay. So then what do I know? I know that this inner product grad f with this vector v, this is going to be sum over ij, ai bj, gij, right? Yes? When I just take the inner product and use bilinearity of the inner product, then I'll get this sum over ij, ai bj, gij, right? And this I can write as an inner product in Rn, right, of the matrix Gij. So let me call that capital J, acting on, let's say, the vector A in Rn, inner product with the vector B in Rn. So this is the inner product in Rn, okay, where A vector is A1 to An in Rn, and B vector is B1 to Bn in Rn. Okay, now this inner product grad f V is the same as dfp acting on V. And we know what df is. df is sum over I del f del xi dxi, right? So, and dxi acting on V will be just bi. So this is going to be sum over I del f del xi bi, right? Okay, so this is the Euclidean inner product of what you could call the Euclidean gradient vector. So if I call this chart phi, so then I have a Euclidean gradient vector, okay, which is the vector with components del f del x1 up to del f del xn. This inner product with B in Rn. Okay, where this Euclidean gradient vector grad phi f, this is del f del x1 is the Euclidean gradient, right? When you think of f as a function on Rn using the chart phi, then it's the gradient vector in Rn of that function in Rn. Okay. So what do we get? We get that this GA inner product B Rn is equal to inner product grad phi f B in Rn. This is true for all B in Rn. Therefore, that implies that G times A is equal to this Euclidean inner product, Euclidean gradient, sorry, grad phi f. So that implies that A is equal to G inverse grad phi A, grad phi f. Okay. So if let G inverse be the matrix G upper ij. Okay. So then this A will be what? This is so then grad f, this we were writing in terms of this vector A as sum over I ai del del xi. So ai is given by this. It's the components of G inverse grad phi f. So this will be sum over I, and inside I'll have a sum over J, G upper ij del f del xj, right? The whole thing del del xi. Is this clear? Okay, so this gives a coordinate expression for the gradient vector field. Okay, in local coordinates, it looks like this. So in particular, this tells you that the gradient vector field is a smooth vector field. Okay. Because these coefficients here are smooth. Okay. Is this clear?
Yes, sir.
Okay. And we have an expression in local coordinates for this gradient vector field. Okay. So that's the gradient vector field. Now, so that's related to the first derivative. If you like, you can think of this as the dual of the first derivative. So the point is, when you have an inner product, right, that gives you a natural isomorphism between the vector space and its dual, right? Between TPM and its dual, the inner product gives you an isomorphism. So under that isomorphism, the gradient vector corresponds to the linear functional df. Okay. So nabla f corresponds to df under the isomorphism from TPM to TP star m given by the inner product. That's all. Is it clear? Okay, I should make a remark here. When I was looking through your midterms, many of you were writing, given a vector v and e, you were writing v star. There is no map from e to e star for a general vector space E. The dual of an element of a vector does not make any sense. Yet many of you wrote that. What does make sense is if you have a basis of E, then you have a dual basis. So if I have a basis EI, then I get a dual basis EI star. That makes sense, where the dual basis is defined by the requirement that EI star acting on EJ is delta IJ. That uniquely, but you need the whole basis EI to define the whole dual basis EI star. Okay. You can't do, given a single vector V, it doesn't make any sense to write V star. There is no such element V star. That doesn't make any sense. But yet many of you wrote some things like that. So please get your linear algebra straight. All right. Given an element V in a vector space capital V, there is no corresponding dual element V star in the dual space capital V star. There is no such thing. Is that clear? This was a mistake I found in many of the papers. So about problem 4. So yeah. Okay. So now let me come to what will be important for us, what's called the Hessian of a function. So we saw in Rn, when we looked at the second derivative of a smooth function on Rn, at each point that was a bilinear function, right? From Rn cross Rn to R, right? It was a bilinear function. So similarly, if I take a smooth function on a Riemannian manifold, then we can define at each point a bilinear functional on the tangent space, which plays the role of the second derivative of f. So define the Hessian of f at P to be the bilinear function. So we'll write this as nabla squared f at P. So this goes from TPM cross TPM to R. So VW, a pair of tangent vectors, goes to what? So you want to take the derivative of the first derivative. First derivative for a Riemannian manifold corresponds to the gradient vector. So you take the gradient vector Now I want to differentiate this in the direction of V. So how can I do that? Well, this is a vector field. I can take its covariant derivative in the direction of V. Okay, so I take nabla sub V of grad F, right? Remember that for a vector field, the covariant derivative only depends on, with respect, I mean, I can, in the first argument of the connection, I can put in a tangent vector, right? So nabla xy only depends on the value of x at the point P, right? So I look at nabla sub V of grad F, then I take inner product of this with W. Okay. Is this clear? Yeah. So this will be bilinear in V and W, right? So this is a bilinear function. Okay. So this is defined to be the Hessian of F. So the first thing to show is that this Hessian is actually like in Rn, this is a symmetric bilinear function. So the Hessian is symmetric. So how do we show this? So let xy be two vector fields on M. Okay. Right. So if I look at nabla squared F, so this will act on the pair of vector fields xy to give me a function, right? So what is this function? This is inner product of nabla x of grad F with y, right? Now, what is the connection I'm using on the tangent bundle? It's the Levi-Civita connection or the Riemannian connection. So that satisfies the metric compatibility property, right? So this I can write as by the metric compatibility, I can write this as x applied to the function grad F inner product y. But then I'll get another term, which is inner product of grad F with nabla xy. So I have to subtract that term. So I have to subtract grad F acting on nabla xy, right? Okay. Yes. So now the first term, grad F inner product with y, this is the same as df acting on y, right? By definition of the gradient vector field, right? Okay. Yes?
Yeah.
Okay. Now, here, remember that what the symmetry of the Levi-Civita connection said? It said that nabla xy minus nabla yx is equal to bracket xy, right? This is symmetry of the connection. So this minus nabla xy, this will be minus, I can replace this by minus nabla yx, right? So this will be nabla yx. And then there'll be a bracket term. So when I take this to the other side as a minus, this also becomes a minus. So then I'll get minus inner product of grad F with bracket xy, right? Okay. Yes. This is by symmetry of the connection. Yeah. Okay. Now what is this x dfy? This is x acting on df acting on y. By definition, that's the same as the vector field y acting on the function f. So this becomes xyf, right? Okay. And then this bracket, this grad f acting on bracket xy, this is df acting on xy. So that is bracket xy acting on f, right? And then I have this other term here, grad f nabla yx. Okay. So what is bracket xy? It's xy f minus yxf. So the xyf will cancel. So what I'll get is yxf, right, minus this grad f nabla yx. And this is y acting on inner product grad f x minus grad f nabla yx. And now I again use the metric compatibility. So I'll get nabla y grad f x, and then I'll get a nabla grad f and nabla yx. That will cancel with this grad f nabla yx. So that will leave me with this. Okay. So that is the Hessian acting on y comma x. Okay. So therefore it is symmetric. Is this clear?
Yeah, it's clear.
Yeah. Okay. So the Hessian is symmetric. So as you can see, the symmetry of the Hessian, it follows from the symmetry of the Levi-Civita connection. Right? That's what we use to prove the symmetry here. Okay.
Sir, I think it's a good time to stop the meeting.
Yeah. So let's stop this session and we'll start a new one. Okay. Let's stop this. Okay. All right. So we've defined the gradient and the Hessian. And we've talked about the change of variable formula for the volume measures. Let me just see what else we need. Yeah, so this is the symmetry of the Hessian. Okay, so now, so since the Hessian is a symmetric bilinear form, we can identify it. So it's a symmetric bilinear form on a inner product space. So therefore, we can identify it with a self-adjoint linear map, right? So that self-adjoint linear map we'll also call the Hessian. Okay, so that's going to be a linear map from TPM to TPM, right? So what is the correspondence between symmetric bilinear forms and self-adjoint linear maps? The symmetric bilinear form nabla squared f acting on VW is given by the inner product of the self-adjoint linear map Hessian f acting on V, inner product with W. Okay. So from the definition of the Hessian, that is the symmetric bilinear form, this linear map from TPM to TPM, it's given by just V goes to nabla sub V of grad f. Is that clear? This is a linear map from TPM to TPM. Okay. Yes, is that clear? Yeah. So we have this correspondence. The symmetric bilinear map, nabla squared f from TPM cross TPM to R. This corresponds to the linear map Hessian f at P from TPM to TPM V goes to nabla sub V of grad f. Okay. Is this clear? Yes?
Yes, sir.
Okay. So now, suppose gamma is a smooth curve. Okay. Then let's look at the function f composed with gamma, right? Okay. So what is the first derivative of this function? By the chain rule, this is df at gamma t acting on gamma prime t. Now, by definition of the gradient vector, this is the inner product of grad f at gamma t acting on gamma prime t. Okay. So what will the second derivative be? If I look at d squared dt squared of f composed with gamma, this is going to be, so ddt of this, so ddt of this inner product, but now by the metric compatibility, right? This is going to be the inner product of the covariant derivative, capital D sub dt of grad f gamma t, inner product gamma prime t, plus grad f at gamma t, inner product capital D sub dt of gamma prime, right? And what is the first term going to be? Well, this grad f is a vector field on the manifold. So if I'm restricting it to the curve gamma and I take its covariant derivative along gamma, then by the compatibility property of the covariant derivative along a curve, this is the same as nabla sub gamma prime of grad f, right? Inner product with gamma prime plus inner product grad f gamma inner product with capital D sub dt of gamma prime, right? So what is the first term? The first term is just the Hessian, right? Nabla squared f acting on gamma prime, okay, plus the second term. So we get this formula, okay, for the second derivative of a function along a curve, right? So d squared dt squared of f composed gamma is the Hessian acting on gamma prime, plus a term coming from the covariant derivative of the curve. Okay, so in particular, if gamma is a geodesic, then this second term on the right hand side vanishes. D gamma prime dt is 0. And so we get that nabla squared f acting on gamma prime is equal to just the second derivative of f along the geodesic. Okay. So notice the Hessian is a symmetric bilinear form. Therefore, by the polarization identity, it is determined by its values along the diagonal, right? Acting on pairs of vectors v comma v, right? So this determines the Hessian, and the Hessian along the diagonal is just the second derivative of the function along the geodesic. Is it clear? Okay. Yeah, so this is like the formula we had in Rn, right? The second derivative acting on v comma v was the second derivative of the function restricted to the straight line in the direction of v, right? And the straight line in the direction of v, that is a geodesic in Rn, right? That is the unique geodesic in Rn with initial velocity v. So we have the analog of that formula in a Riemannian manifold. The Hessian acting on gamma prime is just the second derivative of f along the geodesic gamma. Okay? Is it clear?
Yeah, it's
Okay. So, in other words, so if V belongs to TPM, then nabla squared f VV. This is the same as inner product of Hessian f v comma v. This is equal to d squared dt squared at t equal to 0 of f composed with gamma, where gamma is the unique geodesic such that the initial conditions are gamma 0 equal to p, gamma prime 0 equal to v. Is it clear? Okay. So in particular, if just like in Rn, f has a local maximum at P, then for all V in TPM, this inner product of Hessian f VV, this is d squared dt squared f composed gamma at t equal to 0. This is going to be less than or equal to 0, right? By the one variable calculus. This f composed gamma has a maximum at t equal to 0. So its second derivative is less than or equal to 0, right? Is this clear? So that means that the Hessian, which is a self-adjoint linear map, this is negative semi-definite, okay? At a local maximum. Is this clear?
Yes.
Okay. And also, of course, you can say that the gradient vector field at P has to be 0 because the derivative df P is 0, right? Is that clear? Yeah.
yeah, it's clear. Yeah.
Okay. And so similarly, like we proved in Rn, if say grad f p equal to 0 and Hessian f at p is strictly negative, so negative definite, then f has a strict local maximum at p. Okay, so try and prove this as an exercise. All right. So this is just like what we proved in Rn. Okay. This is an exercise. Is this clear?
Hmm.
Yes. Okay.
Yes, sir.
Okay. So try and prove this. Try and prove this. Okay. So that's about the Hessian. So now I want to come towards defining the Laplacian. Okay. The Laplacian of a function on a Riemannian manifold. So you know what the Laplacian is in Rn, but we can define also the Laplacian on any Riemannian manifold. So for that, first we have to define what's called the divergence of a vector field. Okay, so M is a Riemannian manifold. And say X is a smooth vector field on M. So the divergence of X is going to be a function on the manifold, a smooth function. So how do we define that function? So we saw how to define the divergence in Rn, right? It was defined in terms of the change in volume under the flow of X, right? So similarly, we can do the same here. Now, the only slight catch is M, I'm not assuming M to be oriented or orientable. So on M, to define the volume form, we needed an orientation, right? So the manifold globally may not be orientable, but at least locally, a neighborhood of a point is just a ball in Rn. That is orientable, right? Any ball is orientable. So locally, I have a local orientation on a ball, right? With respect to that, I can define a volume form. And on a ball, there are just going to be two possible orientations, right? So that will just give me two possible volume forms, which are just negatives of each other. So I will have local volume forms. Okay. So we have local volume forms. Which I'll also write as dvol M. So this is defined with respect to local orientation. Okay. So once I have a local volume form, right? So this is unique up to multiplication by orientation at this volume, local volume form just changes sign. That's all. All right. Okay. Then what can I do? Fine. Divergence X. So this will be a smooth function on M. By requiring that Can yes? Hello, can you hear me?
Yes, sir.
Yes, sir.
Yeah, okay, it said my internet connection was unstable. That's why I was just checking. Okay, so what we can do is we take the local volume form, dvol m, and then I take its Lie derivative with respect to the vector field x. Okay, so this is again going to be a top degree form of degree n. Therefore, it is going to be some multiple of the volume form dvol m, right? So that multiple will be a function. That function I define to be the divergence. Okay, so Lx dvol is divergence x dvol. Okay, so this is the same formula that we had in Rn for the divergence, right? Okay, so what we want is this equation should hold for any local volume form. Okay, and the point is this is well defined because if I change the volume form by a sign, then on both the left hand side and right hand side, I just get multiplied by -1. So this function here does not change. Is that clear?
Yes, yes.
Okay, so this doesn't depend on the choice of local volume form or the choice of local orientation, right? Both sides will get multiplied by the same factor -1. So the function div x will stay the same. Okay. Okay. So how do we get a formula for this divergence? So by Cartan's formula, what do we have? We have that div x into the volume form dvol m. This is equal to Lx dvol m. This is equal to dix dvol m plus ix d of dvol m. But this last term here, the volume form is already an n form on an n manifold. So its exterior derivative will be 0, right? It will be an n+1 form on an n manifold. So that is 0, right? So what we get is that div x into dvol m is equal to d of ix dvol m. Okay, so this will give us an easy way to compute the divergence. Okay. Yeah. Okay. So let's work out now a Leibniz rule for the divergence. Okay. So suppose x is a vector field and phi is a smooth function. So and let dvol be a local volume form. Okay. So we want to work out the divergence of the vector field phi times x. And we want to work out some Leibniz rule for this. So let's look at the divergence of phi times x into dvol. So this is by definition, this is by the Cartan formula, this is d of I sub phi x dvol, right? Now, what is the interior contraction? That means in this n form, you get an n-1 form by putting the vector field in the first position, right? And then applying the n form to the remaining n-1 vectors. right? So if I put this phi x in the first position, then by linearity, by multilinearity, the phi will come out. So this is the same as d of phi times ix dvol, right? Okay. Now I can use the Leibniz rule for the exterior derivative, right? This is going to be d phi wedge ix dvol plus phi d of ix dvol, right? Okay. Yes. Yes. All right.
Yes, yes.
Okay, so now what is d phi wedge ix dvol? So this is again an n form, right? Ix dvol is an n-1 form. D phi is a 1 form. Their wedge product is an n form. So therefore it is f dvol for some function f, right? We have to work out what is this function f, right? Okay, so how do I work out this function f? Well, f at a point P is fp into 1, and I write 1 as dvol applied to a positively oriented orthonormal basis E1 to En. Okay, so this f dvol I can write as d phi wedge ix dvol. So that applied to E1 to En, okay, for any positively oriented orthonormal basis EI of TPM. So f of p is d phi wedge ix dvol applied to E1 to En. So now I have to calculate this term, this wedge product applied to an orthonormal basis. Okay. So what I'm going to do is choose my orthonormal basis carefully so that I can compute this wedge product applied to this orthonormal basis. Okay. So first of all, I notice that if d phi p is 0, then of course this wedge product is going to be 0. And so f will be 0 at that point, right? Okay. So I can assume that d phi p is non-zero. So then grad phi at p is also non-zero. So what I do is I choose my orthonormal basis as follows. I take my first vector E1 to be the unit vector grad phi divided by norm grad phi. I can do this because I'm assuming grad phi at p is non-zero. Okay. So this is my first vector E1. Now I extend E1 to a positively oriented orthonormal basis, E1, E2 up to En. Okay, so I just extend this one unit vector to a positively oriented orthonormal basis, E1 to En. Okay, so that means the E2 up to En, these are orthogonal to grad phi. Okay, so I'm going to use that now. So that means that if I look at d phi acting on EI, that by definition of the gradient is the same as inner product of grad phi with EI. And by my choice of EIs, if I is between 2 and n, then EI is orthogonal to grad phi. So this is 0. Okay. Therefore, when I compute this wedge product, what is going to happen? Well, remember how the wedge product was defined. It was defined in terms of the alt map, right? So you had to take the tensor product of d phi and this ix dvol and then apply alt to it, right? Then apply alt to it. Okay. But that means basically I'll look at the tensor product and then I will apply that to all permutations of E1 to En, right? Now, the tensor product means one of the first vector here will go into the d phi and the other n-1 vectors will go into ix dvol. But when I'm taking permutations, if I take any permutation which puts a vector ei where I is in between 2 to n, if that goes into the first spot, right, then I'll get d phi acting on EI, which is 0, right? So those terms will vanish. So the only permutations I'll be looking at are permutations where the first vector E1 is fixed, right? And the other vectors are permuted. Is that clear? Yes. Right.
Yes.
Okay, when I apply the alt, if some of the EIs where I is between 2 and n, if that comes into the first spot, then I will get d phi acting on EI, right? Which is 0. So those terms will vanish, right? So I won't be looking at those permutations. I'll only be looking at the permutations where E1 is fixed and the E2 up to En are permuted amongst themselves, right? Yes? Yes. Is
Yes.
that clear? Right.
Yes, sir, it is clear.
So what happens when I apply Ix dvol to a permutation of E2 to En? Remember that in the alt map, there was also a sign of the permutation, right? And this Ix dvol is alternating. So the sign of the permutation into Ix dvol applied to that permutation, that will be just a constant. That will be equal to Ix dvol applied to E2 to En, right? Because Ix dvol is already alternating, right? Is that clear?
Yes, sir. Yeah, it's clear. Yeah.
Right. So therefore, I'll get finally just d phi E1 into Ix dvol of E2 to En. Okay, that's what this wedge product applied to E1 to En will be. So now what is d phi applied to E1? So that is grad phi inner product with E1. E1 is grad phi divided by norm grad phi. And what is Ix dvol applied to E2 to En? That is dvol applied to X in the first spot and then E2 to En. And what is X? X I can write in terms of this orthonormal basis as summation I goes from 1 to n. Inner product X EI into EI, right? I just expand with respect to the orthonormal basis. But then now this dvol is multilinear. So this will become a sum of terms, right? But if I is bigger than 2, then I will get EI appearing here and also appearing somewhere later, right? So EI will occur twice, but dvol is alternating. So that will give me 0, right? So the terms for I bigger than or equal to 2 will all vanish. So I'll only get the term when I is equal to 1, right? And this first term here will give me grad phi squared divided by norm grad phi squared over norm grad phi. So I'll get norm grad phi into, I'll only get one term from this sum here when I is equal to 1. Then I will get X inner product E1 into dvol E1 to En, right? And X inner product E1 is what? Grad phi divided by norm grad phi. So that norm grad phi will cancel with the norm grad phi here. So I'll just get X inner product grad phi, and this dvol E1 to En is 1. Right. So finally, I'll just get X grad phi, X inner product grad phi. So that means that this d phi wedge Ix dvol is equal to inner product grad phi X into dvol. So therefore, I get that divergence of phi X dvol is equal to inner product grad phi X dvol plus phi, and then see, what was the term I had here? D of Ix dvol. This again by the Cartan formula, this is equal to divergence of X dvol. So my second term is phi div X dvol. Okay, so now both sides are multiples of dvol. So the coefficient of dvol on both sides has to be equal. So that gives me finally the result that I want, that the divergence of phi times X is inner product grad phi X plus phi divergence of X. Is that clear? Yes?
Yes, sir.
Okay. Okay, so using this, we can prove one second. No, so okay, so yeah, so now what I want to prove is to finish is the divergence theorem. Okay, So suppose M is now an oriented Riemannian manifold. Suppose M is oriented, and suppose D is a domain in M with smooth boundary such that D closure is compact. Then for any vector field X on M, we have that the integral over D of divergence of X d vol. Okay, so d vol makes sense because M is oriented now. It's not just a local volume form, it's a global volume form. This is equal to the integral over boundary D of the inner product of X with the normal vector ds, where n is the outward unit normal to boundary D and ds is the volume form of the boundary of D. Okay, so the boundary of D is a submanifold of M, right? It's a smooth submanifold. So I can restrict the Riemannian inner product to the tangent spaces up to the boundary. That will give me a Riemannian metric on boundary D. And then I take the corresponding volume form for that boundary, for the Riemannian metric on the boundary. Okay, so that is what I'm calling ds. Is it clear? Okay. So let's quickly prove this. So first of all, we can use Stokes' theorem. So this divergence X d vol by Cartan's formula, this is d of Ix d vol. So by Stokes' theorem, this becomes the integral over boundary D of Ix d vol, right? So all we have to show is that this Ix d vol restricted to the tangent space of boundary D is equal to X inner product N ds. Okay. So let P be a point in boundary D and let E1 to En minus 1 be a positively oriented orthonormal basis of the tangent space of boundary D. Okay. So from the definition of the orientation on boundary D, this means that the unit normal, outward normal, N, together with E1 to En minus 1, this is a positively oriented orthonormal basis of TPM. Okay. This is how the induced orientation on boundary D was defined. Okay. So now X I can write in terms of this orthonormal basis as X inner product N into N plus some linear combination alpha I EI. I goes from 1 to N minus 1. So now if I look at Ix d vol restricted to the tangent space to boundary D, so that is an n minus 1 dimensional vector space. So when I restrict this n minus 1 form, then it becomes an n minus 1 form on an n minus 1 dimensional vector space. Therefore, it must be a multiple lambda times the volume form of the boundary ds. Okay. So how do we compute this lambda? So lambda, as usual, I can write as lambda into dsp of E1 to En minus 1. This last thing is 1. And now lambda ds is Ix d vol. So Ix d vol applied to E1 to En minus 1 means d vol applied to X and then E1 to En minus 1. And then X I write in terms of the orthonormal basis as X inner product N into N plus these other terms alpha I EI. Right. So I expand this by multilinearity. The first term is X inner product N into 1. I mean, d vol of N and then E1 to En minus 1 is 1, since this is a positively oriented orthonormal basis of TPM. And the other terms are all 0 because I will have EI occurring twice, right? So that means this coefficient lambda is X inner product N. And that's exactly what I wanted. That means that Ix d vol restricted to the tangent space to the boundary is X inner product N into ds. Okay. And so when I substitute that back into this, integral over the boundary Ix d vol becomes integral over the boundary X inner product N ds. And so that's the proof of the divergence theorem. Is that okay?
Yes.
Yeah?
Yeah.
Fine. So we'll be using this divergence theorem again and again. So it's it'll be very useful for us. Okay. All right. So let me stop here. Are there any questions? Okay, then. So we'll carry on next week. Sorry, next Friday. We'll carry on Friday. Yeah. Okay. So see you Friday then. Okay.